Hey, good afternoon, everybody. Welcome to lecture. So the big news is we have an exam coming up on Monday. Exam 1, it's going to cover the things that are described in the syllabus, and those are summarized in this page called Exam 1 info page, which is available on Canvas. There's a module for Exam 1 that includes all the info for it. I've got all of the reference material that you're going to get on that exam. It's going to include tables of spectra information, a list of oxidizing reducing agents that we've been working with in Chapter 12. We got a nomenclature sheet, pKa table, pKa or periodic table. A list of molecules of the day are here except for the last one, which I'm going to put up in Canvas very shortly, but which I have listed on the board. And there's practice exams too. So if you're looking for practice and you've done the ALEX homeworks for the chapters that have been assigned, these are really good practice. The ones from the last 2 times I've taught the class are here. So Fall 24 and Fall 23, Exam 1. The blank exam is there along with a key so that you can check your work and see if you're doing it right. A lot of people find these really helpful. Give them a sense of how well they know the material, and it just serves as good practice. So that's what's coming up. So I want to tell you about the molecule of the day today, the last one in our sequence. Today's molecule of the day is called geosmin. It's this one right here. It's got 2 6-membered rings that are fused together. There's a methyl group here, a methyl group here, and an OH group here, and there's stereochemistry. This is a molecule that's called a member of a class called terpenes, which are natural products. This particular one, this geosmin, is produced by soil bacteria. And if you ever work with dirt or you're near dirt after it rains, you notice there's a particular smell that goes along with after a rain, the dirt smells a certain way. That's because of this molecule. So this molecule gives that wet soil smell after a rain. So they produce it, and then when it rains, it gets aerosolized so you can smell it. And it's a very, very potent smelling material. Human noses can pick it up in very, very low concentrations. And so it's an interesting one for that reason. It's a natural product. It's produced by bacteria, and it's our last molecule of the day. There are 5. This is the 5th of 5. Any questions about molecule of the day? All right, let's talk about the last survey question then, which was a challenging one that had to do with a multi-step synthesis. So there are 3 steps here. First of all, you're given an alkyne starting material, and then there's 3 steps that are given, and you're asked to pick which of these products comes out of that reaction sequence. So what I'm going to do is work through this on the board now, and then we'll talk about this. I'm going to sketch out the steps over on the board, and then we'll work through how to figure this one out. It's 3 steps in a row, so you have to do reaction 1, then reaction 2, then reactions 3. That's what the 1, 2, 3 means. Those reagents are applied in that order. So the starting material is a carbon-carbon triple bond. And the first reagent is H2, and you're told Lindlar catalyst. That's the palladium and quinoline combination that's really good at taking alkynes and stopping at 1 reduction to give an alkene. And it gives a cis-alkene. If you have an alkyne that has 2 R groups on it, this alkyne has an H on one of the ends, so we're going to get an alkene. It's just not going to be either cis or trans. It's just going to be an alkene. That doesn't have easy stereochemistry, so the hydrogen adds across the triple bond, and it gives this first of 2 products. And I'm going to draw this in a way such that you can really see the stereochemistry here. This is one where the molecule, the stereochemistry doesn't matter because it's not E or Z, but I want to just practice drawing the alkene the way you should be drawing it. So whenever you draw alkenes, like when you do them on the exam here, it's really important that you show bond angles that are about 120 degrees. It doesn't have to be perfect, but where you run into problems is if you have a bond angle that's 180 degrees, then you can't tell whether the H's are on the same side or on opposite sides, and then ALEX program will get confused and mark it wrong. I won't know what your answer is on an exam, and I might have to mark it wrong. So just make sure that when you draw an alkene that you've got 120 degree bond angles approximately, and then it's crystal clear exactly what you mean. So H's add across, and the ones I have circled here, those are the new ones that were added. The Lindlar catalyst helps make it happen. So that's step number 1. Then you're told there's a step number 2. So the next thing that happens is this gets put in with MCPBA. That's an abbreviation for metachloroperoxybenzoic acid, and that's one I'd give you the structure of on an exam. But since this was a survey question, you could look it up. It's a peroxy acid, and what those do is they give epoxides. So they react with alkenes and they give epoxides. So in this case, you get an epoxide, and there's 2 different stereoisomers that you get of this epoxide. There's the version of the epoxide that looks like this, that has methyl group on a wedged bond. And then there's another version of this, a stereoisomer that gives the methyl group on a dash bond. So these are the 2 stereoisomers. If the question were ending with 2 steps, you'd want to draw both stereoisomers because they are different molecules and they have, they're not the same, and you really should draw both of them. The last step is lithium aluminum hydride reduction. So lithium aluminum hydride is this really strong nucleophile that adds to electron poor carbons like the carbons of our epoxide here, and it's going to preferentially attack the more sterically accessible one, the one that's less crowded. One of the H aluminum bonds, electrons come out and they go here and they attack that one, and then you get a ring opening step right there. That's step 1 of this 2-step process, and the last step would be treating with water, H2O. So the first step, you get an O- here, and then the water puts the proton on that. So in the end, what you get is this product. I'll draw it with the wedge in place right now, and then we'll do a version of it that doesn't have the wedge, because what we're making here ultimately ends up being an achiral molecule. And it turns out that this one reacts to give this product, and this is not a stereogenic center because the 2 methyl groups are the same. So really this one is going to be drawn in a more simplified form. It's going to look just like this. So the starting material here has a stereogenic center, but the product ends up not having one. So this is the final product, and it's what you get after you do this 1, 2, 3-step reaction sequence. So this is a challenging reaction question because it requires that you string 3 different steps together and get the right answer each time. Otherwise you can't get to the product. It's on the hard side of the difficulty spectrum for reactions that we've looked at, but every single one of these reactions, if it were an individual reaction, I think would be very manageable. So hopefully this stuff looks familiar, and you can recognize like each one of these reagents. Lindlar's catalyst does syn addition to alkynes to give cis alkenes, and then MCPBA peroxy acids do epoxidation of alkenes to give epoxides, and then epoxides can be opened with lithium aluminum hydride. Just as a reminder, all these reactions are described in that table that I've got on Canvas and is going to be on the exam as a reference sheet. So you can look at that, and if you're ever not sure what does a peroxy acid do, it's right there in the table. It tells you makes epoxides out of alkenes. Then every one of the reagents from the oxidation reduction chapter, chapter 12, is in there. So use that as a reference. Get used to practicing with it and get good with it. So that's the molecule, or that's the survey question for today. We had a molecule of the day. We've got an exam coming up. The last thing we have to do is to talk about oxidation of alcohols. That's the last bit of new chemistry that we need to discuss. So we're going to do that now. Alcohol oxidation involves removing hydrogens from alcohols. So let's review what kinds of alcohols we have, because this is important. This affects how they work. There are primary alcohols. These are alcohols that have an OH group attached to a carbon that has one R group and 2 H's. The reason we call it primary is because there's one carbon group attached to the carbon with the OH. You always want to zoom in on that carbon that has the OH bonded and ask yourself how many carbon groups are attached to that carbon. In this case, there's one. Then there's secondary alcohols, which have two R groups attached to the carbon that bears the OH. One there and one there. So that's why we call it secondary. And then the other kind of alcohol is what's called a tertiary alcohol. These are alcohols. I'll draw them over here offset so we can see them a little bit better. They have their OH group on a carbon that's got three R groups. 1, 2, 1, 2, 3. So again, the focus is like, what is going on at the carbon that has the OH group? Does it have one carbon group, two carbon groups, or 1, 2, 3 carbon groups? We call it primary, secondary, or tertiary based on that. The reason this is important is that they display really different oxidation behaviors. Primary alcohols are the most oxidizable because they have two H's that can be removed from that carbon. Secondary alcohols can be oxidized, but just once because they have just one H. And tertiary alcohols, they actually don't oxidize at all because that carbon that is got the OH group attached has no H's. So that's the behavior we're going to see. And we're going to go through and describe the chemistry of oxidation chemistry of primary alcohols, secondary alcohols, and tertiary alcohols. We'll start with primary alcohols. Their behavior is the most complicated because there's two different things they can do. Oxidation of primary alcohols. The first reagent we're going to look at is one called PCC, or pyridinium chlorochromate. If you have an alcohol that has one carbon group attached to that carbon that the OH is bonded to, this is a primary alcohol, you can oxidize it once selectively if you pick your reagent properly. The reagent that we'll use for this application is one called pyridinium chlorochromate. And the way it looks is it's a chromium that's got double bonds to, I'm going to draw it the way that it gets drawn in the book. The chromium has a double bonded oxygen, another double bonded oxygen, a single bonded chlorine, and a single bonded oxygen with a minus charge. And then there's a counter ion that goes along with this, which is a six-membered ring with a nitrogen, a proton, a positive charge, and that's the reagent. The name of this is called pyridinium chlorochromate. I'll put the name up, but you're not going to need to remember the name. Pyridinium chlorochromate. And that's a lot of words to say, so the abbreviation that people use is PCC, pyridinium chlorochromate. So you may see just PCC above the arrow if you're looking at this in a homework, like on Alex or something. And it's a complicated bunch of reagents. There's a lot of atoms here, but the thing that's important is that there's a chromium in the +6 oxidation state, which is a really high oxidation state. That chromium has 6 bonds to electronegative elements, and it really wants more electron density. It's really electron poor. And this is simply the counter ion that balances out the negative charge on this reagent. And the reason that this one is used a lot is that it's soluble in an organic solvent called dichloromethane that allows it to stop at one oxidation of this molecule. So if you look at what's happening here, the big thing is what happens to this alcohol? Well, it goes to form this molecule, which is an aldehyde. So this is the unique feature of this pyridinium chlorochromate reagent is that it's able to take a primary alcohol, which has a carbon and two H's attached to the OH carbon, and oxidize it once, so it leaves one H attached to that carbon, and it generates a new carbon-oxygen double bond. So it does one oxidation. So this is one thing about PCC. PCC stops at one oxidation. Of primary alcohols. So if your goal is to make an aldehyde, the PCC reagent is the one to use. And the table says this. It says what it is, what the reagent is, and then describes it as being useful for oxidizing primary alcohols to aldehydes. The other thing that primary alcohols can do is they can oxidize to carboxylic acids, which is a bigger oxidation type process, and we're going to talk about that next. So this is the other thing that primary alcohols will do, the other oxidation reaction that they will undergo. If you have a primary alcohol and you put it in with any other kind of chromium-6 oxidant, and there are two reagents that you'll see listed because the textbook highlights two different sets of reagents. One of the sets is chromium trioxide, and it is put in with sulfuric acid and water, which are important for getting the reaction to go. But this chromium species is just a different chromium-6 reagent. It's got 6 bonds to oxygen, just like PCC does. But the key is it's in water. That's one recipe that you'll see. Or you might also see potassium dichromate, H2SO4, and water, which is practically, it's pretty much the same reagent. It's just in a little bit different starting form. But if you see this one or this one, the reactions with water, they produce two oxidations, and the product that comes out of this is the carbon that the O is bonded to gets oxidized twice to give a carboxylic acid. So there used to be two H's attached to the alcohol carbon, now there are none. So these oxidize twice. So depending on what reagent the primary alcohol goes in with, it might get oxidized once, or in this case, like in this case, it gets oxidized twice. So you just have to pay attention to what's the reagent and the oxidizing agent, and what kind of alcohol do I have to start with. If you've got a primary alcohol, there's two particular options that could happen. Any questions about this? All right, let's talk about secondary alcohols. And thankfully, secondary alcohols are simpler. They have less complicated oxidation chemistry because they have only one H on the carbon that has the OH bonded. So secondary alcohols, they're abbreviated with a degree 2, oxidize to give ketones. And any chromium-6 oxidant will work. And the chapter and the table list 3 different chromium-6 oxidants. I'm going to draw a secondary alcohol here, and then we'll talk about the products that you can get out of it. So this is a secondary alcohol because the carbon that has the OH bond, it has just one H. And what happens with any of these oxidants, these chromium-6 oxidants, is it steals away that one H, and then you get a carbon-oxygen double bond here, and that's a ketone. The reagents are, you can use PCC, or you can use chromium trioxide, sulfuric acid, and water. Or you can use potassium dichromate, K2Cr2O7, H2SO4, and water. And no matter what you do, you're going to get out the following product. You're going to get out a ketone. And there are many more ways you can do this reaction, not just using one of these chromium-6 reagents, which, by the way, are really toxic and have to be disposed of in a certain way. There's better oxidants. Like this week in lab, we used bleach. That's one good way to do it. There's a lot of oxidants that are better than these. These are just classic cases, examples that are used to illustrate how you can do a reaction. If you're going to actually do this reaction, I would try to avoid using chromium just because of its toxicity issues. But lots and lots of ways to do this. It's easy because the secondary alcohols are simpler than primary. So you don't have to be careful. You just put in pretty much any oxidant you can, and there's just lots of them that'll work, and you can get ketones out really easily. Then one more thing to talk about, one more alcohol type, and that's the tertiary alcohols. And it's going to be a short discussion because pretty much they don't do anything with oxidants. And the reason is they don't have any H's attached to the carbon that has the OH. So this is a tertiary alcohol. That carbon has 1, 2, 3 R groups, carbon groups, and an OH, and there's no H to steal away. So and if you put this in with an oxidant, there's just nothing really to do. There's no H to grab that can lead to an oxidation reaction. These will oxidize if you're brutal enough with them. They will burn and give CO2. That's an oxidation reaction. That's a different kind of mechanism. But they give no reaction with any of the oxidants that we see in chapter 12. So I'm going to say these resist oxidation. So if you see a tertiary alcohol in like the homework and it says what happens when you stick it in with this chromium-6 reagent, there's like usually a box on the bottom that you check for no reaction because they just don't do it. So any questions about alcohol oxidation? This is just managing what happens with alcohols when you put them in with 3 different oxidants that we've got in our list. Okay. Let's do some review. So this is from 2024, exam 1, question 15. There's a whole bunch of questions that ask about different oxidation and reduction reactions. The first one is one where you're given a 5-membered ring with an alkene in it, 1-methylcyclopentene, and the other reagent that you're given is this material that's got a benzene ring with chlorine on it, and then this. So hopefully you recognize this is a peroxy acid. This is actually MCPBA, meta-chloroperoxybenzoic acid. The key feature is that it's got this peroxy acid functional group in it, and that reacts with alkenes to give epoxides. So this is going to be really similar to one of the ones that we did in the survey question, where you just have to figure out what kind of epoxide am I going to get. And this is one where we're going to get 2 different stereoisomers, and you should draw them both. So the way epoxides work is the double bond gets replaced by an O that bonds to each one of the alkene carbons. So the way to think about this is the basic connectivity. An O ended up bonding to each of the 2 alkene carbons, and you get a triangle with an O in it, an epoxide. If you just drew that, you get a good chunk of credit. But the problem is you need to show some stereochemistry here. And the key thing is that you need the oxygens needs to be bonded to the carbons of the ring in the same direction. In other words, the oxygen is bonded to the same face of the alkene on both carbons. So you have to have two wedges coming to the oxygen or two dashes coming to it. And then the methyl group that's here has the other stereochemistry. It's got a dash bond orientation. That's one. That'd be like if the MCPBA were to come in from the top face and attack this way, you'd get this product. The other possibility is MCPBA could approach the alkene face from behind the board, in which case you get the stereoisomer of this, and that product would look like this, where it's still got an oxygen attached, but there's dashed bonds to it, and then the methyl group is going to be on a wedged bond. So that's the first one. And the product, the question also says, it gives you a little hint, I suppose. It gives you that here's another product that gets produced. This is a carboxylic acid. This is the product that you get when the MCPBA does its reaction and epoxidation happens. The peroxy acid becomes a carboxylic acid. But these are the two things you needed to draw. If you got an epoxide in there, you got most of the credit for it that semester. Now let's take another look at another one of these. The next one starts with an alkene that's in the middle of a scheme, and one of the arrows is going left and the other arrow is going to the right. So the alkene in the middle is a cyclohexene with two methyl groups on it, here and here. And there's an arrow going to the left. Always follow the direction of the arrow. It's saying this is reacting with something to give something that goes in a box over here. And we're told hydrogen and palladium on carbon. That's hydrogens that are going to add to the double bond, and that's the catalyst that makes it happen. And if you just drew this, you'd get a good chunk of the credit for the question if you got that hydrogen adds to the carbons of the double bond to give this. You know, that's the connectivity. That tells a lot. But the one thing that's missing is the stereochemistry and the fact that when these reactions happen, the two hydrogens add to the same face of the alkene, either from the top face, in which case you give them wedges, or from the back face, in which case you give them both dashes. So you have to get the stereochemistry in there to get the full credit. So I'm going to pick just one of the two options. In this case, they're both identical because the molecule is the same if you flip it over. If it gets attacked from the top face or the bottom face, in this case, you get the same product. It's not a different molecule. So this one is the one structure you need. You could also draw it another way. Yeah, question? If you reverse the wedge. Yeah, so the question is it okay to draw it this way? And the answer is yes, because it's the same molecule, actually. If you drew them both, I would just probably put a note on your exam saying, these happen to be the same in this case, but I wouldn't deduct points for it. If the alkene that you're starting with isn't symmetrical, you're going to get two stereoisomers that you would need to draw to completely answer the question correctly. So either one of those in this case is fine. You can put them both down, but you don't have to. In a lot of cases, though, if it's a chiral molecule, you would need both. There's another question. You would in this case because it's implied, yeah. You wouldn't, so in other words, if you just draw a skeletal structure with the two dash bonds or the two wedge bonds, yeah, because the representation, it's assumed that there are hydrogens on the dashes of the wedges that you're not showing, so that's fine. And if you do that in Alex, it will also give you credit for it. So as long as the double bond is gone and you've got wedges or dashes, you're good. Yeah, good question. Then there's an arrow that goes to the right, and this right-pointing arrow is asking you to consider using either KMnO4 with hydroxide, water, or it says you could also use in a two-step process osmium tetroxide, and in the second step sodium bisulfite. And if you didn't know what these reagents were, look them up in the table that I've got for you. And the table says, if you look at what it's used for, converting alkenes into syn-diols. Syn-diol is 1,2 alcohol, so each carbon of the alkene gets an OH group, but they're on the same face, so they point in the same direction. So in this case, there are two ways to draw this. You can either draw the OH groups with a wedged bond orientation, and the methyl groups on dashes, or equally correctly, and in this case exactly the same molecule, is described by putting the OH groups on dashes and the methyl groups on wedges. They're the same because the molecule has a mirror plane of symmetry in it, and you can just flip one over and you'll get the other. Like in this case, if you took this molecule with the alcohols pointing down and you flipped it over, the alcohols will be pointing up. This one and that one are superimposable. So you need two structures. You can draw them both, but it's the same molecule in this case. Yeah, question? Can you do an example where they're not? Sure, yeah, let's go through one of those, because yeah, this is a version of the question where you get a stereoisomer. So yeah, let's take a look at this. So here is a molecule that's got a double bond in a ring, and it's not the only case where you get stereoisomers, but they're just easier to see when you have a ring. It's really clear that the OH is added from different faces. So let's do this one, and let's do the potassium permanganate conditions. You can use the osmium tetroxide conditions, and you get the exact same thing. But what happens is two O's add to either the top face of the alkene or the back face from behind. If they add from the top face, the face closest to you, the OH groups get delivered with a wedge bond orientation. The reagent comes in from the face closest to you, and then the methyl group, as the OH groups are added, the methyl group gets pushed away, so it ends up on a dash bond. So that's one of your two possible products. The other possible stereoisomer is the one that you get if the OH groups or the O's get added from the backside, from behind the board, in which case they're going to get added with dash bond orientation. And then it's the methyl group that gets bent out of the plane and ends up pointing up. These you have to draw both structures because they're not the same. This and this aren't superimposable. They are enantiomers of each other. And if you just drew one of them, there'd be some penalty for not drawing the other one. If you drew them without any stereochemistry at all, there'd be a little bigger penalty because you didn't recognize that there's actually a stereogenic center here and a stereogenic center here. And it's important that you show the OH groups pointing in the same direction, because that's the way this reaction works. And in both cases, the OH groups point in the same direction. They're both syn addition diols. So that's dihydroxylation. This exam is hitting like all of the different like reaction classes, so it's trying to be comprehensive about it. Let's take a look at the next question in that series. Oh, hey, this exercises some of our recent alcohol oxidation knowledge. In the middle of the scheme, there is an alcohol. And there's an arrow going to the right and an arrow going to the left. And above the left pointing arrow is K2CR2O7, H2SO4, and H2O. And over the right pointing arrow is this molecule, and there is a ring with a nitrogen, a proton and a plus charge on the nitrogen. This is the PCC reagent. And this is potassium dichromate. So first thing to understand is this is a primary alcohol. So if you're facing oxidation reactions, just make sure that you first figure out what kind of alcohol you're dealing with, because that determines what sorts of reactions it can do. Since it's a primary alcohol, it has two H's that can get removed. We're either going to remove one of them and make an aldehyde, or remove both of them and make a carboxylic acid. And so what you got to, well, you don't even have to remember it. You just have to look in the table and see what does PCC do. It removes one H and gives an aldehyde. So primary alcohols become aldehydes. So the product of this reaction would be that the oxidizing agent stops at one oxidation, it removes one of the two H's and the H on the O, and you get an aldehyde. And that's the big reason people use PCC a lot of the times. It's one of the few reagents that can do this selectively. Aldehyde. Then if you use the other chromium-6 reagents, potassium dichromate or CrO3, they'll both give you the product that's been oxidized twice. So the one that's got a carboxylic acid. So that's different chromium-6 reagents working on a primary alcohol. Would you like to see, yeah, a question?
Is the one on the right and the left, like if you would have swapped, like where the double bond is on top, if you just flipped whether the OH and the double bonded O were gone to.
Are you talking about this reagent?
Products for both sides. Like
Okay.
if you would have taken the double bond oxygen and put it on the bottom and put the single bonded alcohol, is that fine too?
Yeah, so the question is it okay to draw it this way? And the answer is absolutely yes, because it's just a rotation of the same molecule. You're allowed to do that. You can choose to draw it in whatever conformation you want, unless you're asked specifically for some reason to put it one way. This is actually just, it's the same molecule, just rotated around. But as long as you have it connected properly, you're going to get the right answer. Alex recognizes it. I'll recognize it. It's just the molecule viewed from a different perspective. So, and that's okay. Mm-hmm. Yes?
I have a question on 5.
Okay, on that same exam?
Yeah.
Okay, so this is a question about number 5 on that 2024 exam, which I have the copies with, or I'll look it up. So I have it on here. Okay, so this one's asking about some isomeric ketones.
It was mainly about like on the conjugated and non-conjugated part.
Sure. Let's talk about conjugation and how it affects frequency. So this is a question about how can you differentiate two isomers that are very similar looking but have some different spectroscopy traits. Here's one of the two isomers, and here is the other isomer. And they are very similar looking. The difference is, I gotta adjust this. So this is question 5 off the 2024 exam 1. And how do you tell these apart by spectroscopy? They have the same carbon skeleton. It's just the location of the double bonded oxygen is different here versus here. So the big thing about these two is that one of these is conjugated and the other one is not. Normally, a ketone carbonyl, like this type right here, shows up at around 1710 inverse centimeters. That's a frequency that's just normal for ketones, carbonyl like that. Over here, this one is different because it has a double bond, single bond, double bond pattern. That is what we're going to learn to call conjugation. We're going to study conjugation after exam 1. We get a couple of chapters in, we're going to talk about this. But anytime you have a pattern like this where it goes double bond, single bond, double bond, the double bond here gets a little weaker because of this. It shares a little bit of its bond character, double bond character with this bond, and it gets to be a little weaker and a little longer, and its frequency gets to be a little lower. So one like this would have a frequency of maybe about like 16, I'm just kind of getting, making up a number here, but I'm going to say 1685 inverse centimeters. And I'm going to say, just the note here is frequency is lowered by conjugation. And this is one of the multiple choice answers, or actually there's a bunch of answers A and B about this. It's asking which of these would have a strong absorption near 1710? Well, it's this one. And then another question says which one would have a strong absorption at 1690? Well, it's got to be this one. I guess my estimate here was a little off by 5 wave numbers, but you can definitely distinguish. This one's lower because it's got the conjugated carbonyl. Okay, and then as long as we're on this one, which one of these would give a strong peak at 43? And then there's another one that give a strong fragment in the mass spectrum at 105. So really what this question is asking about is like alpha cleavage. So this molecule, if you broke the molecule off here, this piece weighs 43. And it's an alpha cleavage type process because there's an alpha and beta position there. So that's one of the ones that's in the table of common mass spec fragments. So you pick that out. 43 is very typical of this molecule. This one has alpha cleavage right here. And this part of the molecule, if you add up the masses of these things, this weighs 105. That's m to z. It will give a peak at 105 m to z, mass to charge ratio. So that's another way you can distinguish these. If you have a mass spectrometer and you get a mass spectrum of these, they would both have the same molecular ion mass, but they would have different big fragments. Big base peaks would be in really different spots. So either by IR spectroscopy or mass spectrometry, these can be distinguished. All right. Is there a follow-up question?
Oh yeah. So like when you're like dividing it for like alpha cleavage and stuff like that, does the radical like usually have a bigger piece or something? Like
well, okay. So the question is do you is there any pattern to alpha cleavage other than just alpha and beta? It breaks between them. No, not really. I mean, you can't count on one piece being the big piece and one piece being the small piece. What you can count on is this piece, the piece that goes with the heteroatom, that's going to be the cation. So you see a cation at 43. Here are the pieces, exact pieces that you get. You get this piece, which has a resonance structure that looks like that. So these fragments weigh 43 and they give a peak. And then the other piece here would be this benzene ring with the CH2 group on it, and the CH2 has a dot. And this weighs 91, but you don't see a peak at 91 because it's not charged. Remember, mass spectrometry, if you're going to see a peak, it has to have a plus charge in it. Otherwise, the mass spectrometer can't move it around. It never gets detected, never makes it to the detector. So this is invisible. You don't see a peak for it, but you'll notice it because you'll see the molecule getting 91 mass units lighter. So you know something 91 broke off and floated away, and it just happens to be this piece. So that's a little reminder about mass spectrometry. Let's see what else we can do here. We got a few minutes left. Let's see. Yeah, do you have, I can do requests too. Yeah, do you have a request for a question?
Can we do just an example of an HNMR?
Sure, so proton NMR, how can you figure out, what is going on with it? All right, so, okay, here's one that's interesting. Off of the 2023 exam, number 14, there's an unknown, solve the unknown question, and there are some text information that's given to you. You're not given any spectra exactly, but you're given a lot of information from spectra. So let's work through this one. So this is from the 2023 exam. This is number 14. And we're given a bunch of information. We're told by high resolution mass spectrometry, it has a formula of C3H8O2. The IR spectrum shows only alkyl pieces. It doesn't have any double bonds of any kind. It just says the functional group region of its IR spectrum showed only peaks from sp3 hybridized bonds. So C sp3 to H bonds. So it's kind of a boring molecule. It's got to be just an alkane. And then the proton NMR showed two singlets. Singlet at 4.6 parts per million with an integration of 2 H's. And then there's another singlet. This one's at 3.4 parts per million. And this is representing 6 H's. So when I look at this, I look at that part per million region, and I think this is a region of the spectrum where it's probably a proton on a carbon that has some kind of electronegative Z group. That puts these in this 3.5 part per million region. And we happen to have oxygens in this molecule, so I think that's probably what's going on, is the protons that are represented by this singlet are probably on the oxygen. And there's 6 of them, which to me suggests a couple of identical methyl groups. So what I'm thinking when I look at this information is I'm thinking I have a couple of pieces that are like this, 2 identical OCH3 groups. And that would account for a big chunk of the molecule. So that would be these right here. I'll call this signal A, and I'll call this signal B. So these would represent the B signal. And they'd be singlets because they're attached to an oxygen and not next to anything else. Then we have to figure out what these are. This is 2 H's, and they are at 4.6. So this is even more deshielded. These, you might even think, oh, carbon-carbon double bond, but we know we can't have any of those. And if you did degrees of unsaturation on this equation, you would get 0, which I'll give you the formula for that, but it's 2 times the number of carbons minus the number of hydrogens plus 2 divided by 2. So there's no double bonds in the molecule. What this must be is, and if you take a look at what we've used over here, we've used 2 carbons, 2 oxygens, and 6 hydrogens. What's left is 1 carbon and 2 H's. So there's a CH2 in there. That's what this is telling us, is basically we have a CH2, and we're not told what's next to it, but got to be some things that are deshielding it a lot. So these are 3 pieces that we have. We've got this piece, which makes 2 bonds. We have each of these pieces, which makes 1 bond. And so what you want to do is, once you have all the pieces, and when we add up all these atoms, we can see it's got the right formula. We've accounted for everything. Then we just have to put it together. So we put the CH2 in the middle, because it can bond to 2 things, and you put a OCH3 on each side, and the molecule has a mirror plane of symmetry that runs through it, which is why the 2 methyl groups are the same as each other. So that's how you might solve this one. At least it's the things to think about that would help you get there. And just before you go, if you're in the lab course, the lab homework for experiment 2 is really good for spectroscopy help. So even if it's not, if you're trying to practice for NMR on the exam and IR, check out that homework. It's got a lot of really good problems. So, okay, I will talk to you next. Have a good day. See you Monday.